Hi everyone, this is K. Vamshi from EC Decision, having rule number 04M7. So today I want to discuss about the monopulse comparators under the subject IC applications as a TikTok topic of the we discuss about the applications of the monopulse comparators. So coming to the introduction, in radar system antennas serve dual purpose like transmitting and receiving the information required for searching or tracking a target. So some technologies used for this antenna like lobe switching, conical switching, and monopulse tracking. Here the monopulse tracking technique is useful because it offers high speed, high accuracy target estimation using a single pulse. So a feedback network known as multiple monopulse comparators is required to process the collected information, and it also helps the determining the monopulse tracking performance. So here these are some techniques where we can process the received information, but monopulse tracking is having high speed, high accuracy, and target estimation, as it has some benefits. So we use this method in monopulse comparator to process the collected information at the receiver. So and it also help us to track the performance of the monopulse comparator. It is also known as sum and difference network. So it requires a set of 2 or 4 similar antennas, and depending on the tracking axis to determine the angular position and distance of a target. So based upon the construction and angular position and tracking axis, we require 2 or more similar antennas, also known as single planar antenna and double planar antenna. You can see further. So the latter has the advantages like lightweight, low volume, simple structure, and ease of fabrication, but the disadvantage is low power handling capacity, as it consumes more even more power consumption. It has some advantages like a simple easy to make, low space, low weight, simple structure. And the principle under which monopulse comparator works as the basic is which can track within a single plane or 2 planes simultaneously. Here you can see the diagrams for the sum and difference for the single plane monopulse comparator and double place monopulse comparator. In the first diagram, it has 2 antennas which gives the sum of 2 information from the 2 antennas. Also we can difference the information from the 2 antennas, like where we use azimuthal or elevation difference. In the second diagram, here you can see the 2 antennas which has the previous sum of 4 antennas like A plus B plus C plus D and A plus B, C minus B plus D. So here you can see the difference of information like azimuthal difference and matched load, which are defined as A plus B minus C plus D as azimuthal difference, and matched load as A plus D minus B plus C. So the single plane comparator track the target in either the elevation or azimuthal plane. For dual plane tracking, we use both 90 phase delay. Like we define the sum as A plus B plus C plus D, where A plus B plus C plus D is a information collected antennas A, B, C, D, and azimuthal difference as A minus C minus of B minus D, and where elevation difference is as A minus B minus of C minus D. And there can be 4 cases where we can target the location of information. Like in picture A, here you can see the azimuthal difference as 0 and elevation difference as 0, as the target is equally divided into 4 parts, where coming to the B, azimuthal difference is non-zero, as horizontal separation is not symmetric. Where coming to the C diagram, vertical partition is not symmetric. So elevation difference is non-zero and azimuthal difference is 0. We coming to the last picture, you can see the partition of the target is overall not symmetric. So azimuthal difference is non-zero and elevation difference is non-zero. So coming to the monopulse comparator using branch line coupler. Here you can see the two diagram for 3 dB 2 branch line coupler and a single plane monopulse comparator with 3 dB 2 branch line coupler with 90 phase delay time. In the first picture we don't have the delay, but we take the 90 degrees phase delay. So it is a single plane monopulse comparator using 3 dB branch line coupler with 90 phase delay line. So monopulse tracking in a single plane can be performed using two similar radiating antennas placed horizontally or vertically depending on the plane in which tracking needs to be done. So the characteristic impedance Z0 of the input and output port lines is 50x, and the impedance values of the main line ZA and branch line ZB are calculated using the even odd mode analysis discussed in the even odd mode analysis of two branch line coupler, which gives the ZA equal to 35.35 and ZB equal to 50x. So this impedance of a main line and branch lines can be calculated using the principles of theory of even and odd mode analysis of a two branch line coupler. Here you can see the matrix describing the impedance of a monopulse tracking single plane comparator. So another parameter we calculate as null depth. So it is a minimum amplitude level that the antenna pattern generator will produce. The maximum null depth is odd wave specific and typically greater than minus 80 dB. So in practically or theoretically, the maximum null depth is minus 80 decibel, but here you can get the minus 3 dB null depth. So null depth can be calculated using the formula 20 log of output amplitude at the difference port and to the ratio of output amplitude at the sum port. As a null depth of a minus 33 dB has been calculated at 9.5 GHz. So we get the gain of null depth as minus 33 dB at the frequency of 9.5 GHz. So here you can see the graph of a null depth at different frequencies, like it describes the frequency at input and output ports and transmission coefficient and the phase response and the isolation between the ports. So these are the four graphs describing the different terms like VSWR at input and output, transmission coefficient at B, and phase response in third graph, and isolation between the ports in the fourth graph. So coming to the dual port monopulse comparator using 4 dB branch line comparator with 90 phase delay lines. So 4 dB branch line couplers with 90 degrees phase delay lines can be interconnected as shown in figure 6. So to form a dual plane monopole comparator, ports 1 to 4 are input ports and ports 5 and are output ports. Port 8 gives the sum and port 6, 7 gives the elevation and azimuthal difference respectively. So these ports are defined at as different functions, like input ports and output ports, and 8 gives the sum and 6 and 7 give the azimuthal and elevation difference respectively, and port 5 gives the diagonal difference which is not required and it has been terminated with a matched load. However, this fourth port can either be connected through a movable short circuit to comparator for the compensate for the performance degradation due to any fabrication error if present, or it can be used as comparator at second at different frequency as explained in it. So here you can see the matrix defining the monopole comparator impedances as and this is the diagram of dual plane monopole comparator designed using 4 dB with 2 branch liner with 90 degree phase delay lines. So and monopulse comparator with using rat race coupler, like a single plane monopole comparator using a single rat race coupler. These are another classification of a monopole comparator. Like you can see the diagram for the a single plane comparator monopole comparator using a rat race coupler. So and another matrix define the monopole comparator impedances. So here you can see the similar graphs we described uh, above before. So here is the table which compares the different plane and monopole comparator configuration, like dual plane, single plane, rat race, which having the design detail like 3 dB 2 branch line comparator with 90 phase delay line or without 90 phase delay line, like and rat race 4 dB 2 branch line couplers with 90 phase delay lines with 4 rat race couplers. So here you can see the waveforms and picture of a comparator where A describes the fabricated monopulse comparator with 4 race couplers. Here you can see the 4 rat race couplers designed in the material, and B and C here B describe the input and output ports, and D describe the isolation between the two ports. So coming to the conclusion, a monopole comparator designed using rat race couplers has the advantages of wider bandwidth and better null depth compared to the when using 2 branch line couplers. So finally, rat race couplers are more efficient and used more widely than 2 branch line couplers because it has advantage of wider bandwidth and better null depth compared to the branch line coupler.